triangle trigonometry. And pretty much everything we're doing has to do with right triangles until the very end. And we want to be able to simplify radicals today because it's not okay a lot of the time. I don't know why. You know, this is where I think that math hasn't caught up with reality. Square root of 160, we can approximate in our calculators. And it is a little bigger than 12, okay? And that's great, but this is an approximation, and our job is to be able to simplify it so we still get an exact answer, but it is as simplified as possible. I wish they would just let this go, but it keeps popping up in your M-STEP stuff and SAT stuff, and I'm just like, why in God's name, why? Plus, you know what? My calculator, my fancy schmancy white calculator, that's half the cost of these calculators, will simplify radicals all by itself. All right? So my calculator can simplify a radical. So right now I think that you guys have a deficiency. Your calculator doesn't do that. All right? So this calculator does. It's totally awesome. And it's only like $45, as opposed to these, which are $180. So it's an awesome calculator. If you want to get one, they're great. Here we go. So we want to be able to simplify radicals and make it as simple as possible. It's kind of like reducing a fraction, but it helps to go through our perfect squares. So right here, I think you all know what 1 squared is. We're going to start with, like, I don't know, 5. 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10, 11, and 12, 13 squared, 14, 15 squared, 16, 17 squared, 18, 19, and 20. Because I think that you know what 4 squared is. What's 4 squared? 16, great. Will you please complete the table? Will you write in all the answers? Which you should know the top line, I hope, very easily. So go ahead and take a second and figure out what all of the powers are. And then you need to use your calculator. Please use your calculator. Okay, so we have a list of the first 20 perfect squares. The pink numbers are what are called the perfect squares. And the reason they're called perfect square numbers is because I could imagine making a shape of a square, and inside of it, if I was thinking about 25, there would be, I could arrange little, the little unit cubes, 3, 4, 5, 1, 2, 3, 4, 5. So perfectly, 25 little unit cubes will arrange themselves perfectly into a square. And that square has what side lengths? 5 and 5, yes. And so this is why they're called perfect squares, because all of those pink numbers will arrange themselves into quite literally a perfect square, okay? There's no reason we call it that except it really is just literally a square, all right? And so we have their square roots, which happens to just be the side length of the square. And that's what we're trying to figure out. When we simplify a radical, express the radical in simplest radical form, we are trying to figure out, hey, what is the biggest perfect square in 160? So what we're going to do is we're going to break down 160, and there's a multitude of ways to do this. But right off the bat, 160 is what times what? It ends in a 0. 16 times 10. Yes, it is. 16 times 10. Now, I like that. 16 happens to be a lovely perfect square. That is a lovely perfect square number. And because of that, we can simplify it. When we have a giant radical, we can split it into 2 baby radicals. The square root of 16 times the square root of 10. And lo and behold, what is the square root of 16? 4. Yeah, it simplifies. So that's what we look for. We look for those perfect squares. So in your calculator, you can check what is the square root of 16? It's 4. And because it simplifies super nicely, that's what we want to have. Now, how do I know when I'm done? Well, when I look at 10, break down 10 for me. What are 10's factors? 5 times 2. Is 5 a perfect square? No. Is 2 a perfect square? No. Okay, so it doesn't go any further. So you always have to check what's remaining under the radical to see, does it have any perfect squares remaining? Okay. Let's look at 192. Oh, 192. What are some factors of 192? Hint. It ends in a 2. What must it be divisible by? Yeah, okay. So 192. It ends in an even number. So it must be divisible by 2, all right? So there we have 96 times 2. 96 times 2 will give me 192. 96, also even, okay? Which means it's also divisible by 2, all right? So let's see, that would be, if there's another 2 in there, could I do 192 divided by 4? 4, 6, oh, let's see. You know what I want to do? Here's another way. When I get to a number that's kind of big, kind of crazy, maybe I just want to divide by perfect squares. Let's see, 192, let's see, is there 81 in there? No, not even. Let's see, 192 divided by 64. Ooh, that's very good. Okay. So when the numbers get pretty big, having this list of perfect squares is really quite handy. So it turns out that 192 happens to be 64 times 3, which of course I can split apart into 2 little baby radicals. Square root of 64 times the square root of 3. And what is the square root of 64? 8. It is the base. 8. And the square root of 3 is going to just stick on the end here. What operation is between the 8 and the radical 3? They are being multiplied together. Just like up here, all these numbers were multiplied together. This is saying it's 4 times radical 10. Here we have 8 times radical 3. So it was multiply up above. It carries multiplication all the way through, okay? Really important to realize. All right, what do you want to do with 128? How do we break that down? Divided by 2. 128. Maybe I should divide by 4, just because 4 is a perfect square. 4 times 32. Let me see if there's something bigger. 8 is, well, 64 would be a perfect square. 8 is not a perfect square. 16 is a good one, though. Ooh. Oh, I think I can go even bigger. 128 divided by 36? No. 128 divided by 64? Ooh, that's the biggest. So I really want the biggest perfect square, and it happens to be 64 times 2. 64 times 2 is 128. Oh, I should just divide it by 2 first. Wow. Yeah, you were going to do it? Okay. Yeah. Oh, well, no, I would have, yeah, we're good. You get better at it the more you practice this. So, what is the square root of 64? 8. So the 8 simplifies, and the radical 2 tacks on the end. All right. So maybe I don't like that method very much because I think finding perfect squares is hard. 54. When I think about 54, so I'm going to show you just another way to do it. Looking for perfect squares is the fastest and easiest method, but you got to be good with your perfect squares. But breaking things down into primes is also totally fine. All right, so I'm going to show you another way to do this. 54 is what times what? 9 times 6. So you can break down your factors into any factors you want, and what we're going to look for are just matches, okay? We want to find pairs, and I'll talk about that in a second. We want to find pairs. So can I break apart 9? 9 is what times what? 3 times 3, okay. And then 6 is 3 times 2, okay. So what I've done is I've broken this down into prime factorization, all right? Prime numbers, like 3s and 2s and 5s and 7s, okay? So I've broken this down into its prime factors, and when we're taking roots, there's an invisible 2 inside the little elbow. That's called the index. It has an index of 2, and it says, I'm looking for 2 of a kind, all right? So if I have a pair of, say in this case, I got a pair of 3s, then I can take the root out of it. So what happens is 1 gets killed and 1 escapes. So a 3 gets to escape the radical. And do we have any more pairs? No. And so what stays behind the radical is 3 times 2, which is 6. Now, I love this method, and when it's Algebra 1, this is how I teach it, because it works for whatever the index happens to be. So right now we're practicing square roots, but next year in Algebra 2, you're going to be doing cube roots and fourth roots and fifth roots. And this method works every single time. A cube root, we're looking for 3 of a kind. A fourth root, we're looking for 4 of a kind. All right? And so if you break it down to your primes, you're always going to get the right answer. All right? Let's try again with 147. Again, I want to break down 147. 147, ooh, I know that this is divisible by 3. How do I know it's divisible by 3? Not because it's odd. The sum of the digits is a multiple of 3. If you add 1 plus 4 plus 7, the sum of the digits, 1 plus 4 plus 7 is how many? 12. And 12 is divisible by 3, therefore 147 is divisible by 3 as well, okay? So you can add up the digits. And so, let's see, 147 divided by 3 turns out to be 49. So we have 3 times 49. And then, of course, 49 breaks down into 7 times 7. And once again, if I'm doing my square roots, this is its prime factorization. I'm looking for 2 of a kind. I got a pair. 1 dies and 1 escapes. So the 7 escapes the radical, and the 3 doesn't have any friends, so they can't escape. All right? 7 radical 3. So really there's lots of ways to do that, but that's the one I like the best. Okay, so now that we've got a couple of ways to look for square roots. We're going to practice. Here we have radical 8. There's an invisible multiplication sign there, times radical 24. But again, I could multiply these together. I could say, hey, they're both under a radical, so I could do 8 times 24, but then I just get a bigger number. So I think I'm just going to keep breaking it down. We want to simplify these, make the numbers as small as possible. So I'm just going to keep breaking it down here. 8 breaks down into what times what times what? 4 times 2. And then the 4 breaks down into 2 times 2. So 8 is 2 times 2 times 2. 24 is what times what? 12 times 2. Okay, but I got to break down the 12. 4 times 3. All right, I got 4 times 3. So here's the 3. And the 4 breaks down into 2 times 2. Okay, and then times another 2. All right. So I just broke that big number down into its prime factorization. Let's double check. 2 times 2 times 2 times 3 times 2 times 2 times 2. And I get 192, which was the 8 times 24. So we did it right. We broke it down into its primes. And again, what we're looking for are 2 of a kind. If we have a pair, one thing escapes. All right, I have a pair of 2s. One escapes, and 1 is killed. So a 2 comes out. Do I have another pair of 2s? Yeah, I do. So here's another pair of 2s right there. 1 gets killed, and 1 escapes. Do I have another pair of 2s? I do. I have another pair of 2s. 1 gets killed, and 1 escapes. What do you suppose these 2s do when they're all escaping together? Combined by addition or multiplication? Multiplication. Everything is multiplied. It's still going to be multiplied, okay? 2 times 2 times 2? 8. Radical 3. All right? So simplifying radicals is really just about breaking them down. I think the prime factorization is an easy way to go. Here we go. 14 and 35. Breaking those down. 14 is what times what? 7 times 2. And 35 breaks down into? 7 times 5. Yeah, all right. And hey, that's the prime factorization. It doesn't go any more than that, right? All right, do we have some pairs? Yeah, we got a pair of 7. So 1 gets killed and 1 escapes. So we get a 7 on the outside, and then what stays on the inside? 2 and 5. The 2 times 5 is 10. So we're done. Okay. Personally, I like prime factorization. I just think it's easy. Right here it says, what is the product? What does product mean? It's the answer to a multiplication problem. It means multiply. What is the product of 6 radical 8 and 3 radical 24? So this is written out in words, but it's 6 radical 8 times 3 radical 24. So we have 2 different types of numbers here. I want to say that everything here, this is 6 times radical 8 and 3 times radical 24. Some of the numbers are regular numbers, and some of the numbers are totally radical. All right? They don't really mix all that well, okay? But we can multiply our regular numbers together. What is 6 times 3? 18, okay? And then under the radical, we have 8 times 24. And again, I don't really want to multiply those together because when they're under a root, we want to make them smaller, okay? So I'm going to break those down now. Hey, 8. I think 24 has an 8 in there, doesn't it? 8 times 3. See how I did that there? There's lots of ways you can break numbers down because I'm just looking for a pair. So we have a pair of 8s now. So 1 dies and 1 escapes. What do I do with the 18 and the 8? Multiply. Yes, everything is multiplied. So 18 times 8 gives me 144. And then what's in the radical? The 3 stays on the radical. All right. Any questions so far? All right, so what we want to remember here is that numbers that are plain can multiply together, and numbers under a radical, they can work together, okay? So same thing here, but now we're doing some division. I have two baby radicals. Well, it turns out if we're dividing and they're both under a radical, I can put them under a giant radical, sort of the reverse of what we were doing. So it becomes 640 over 5, all under a giant square root. And now I can just clean up. What is 640 divided by 5? 128. So it becomes the square root of 128. And then I need to break down 128. All right, 128. Let's see, I know it divides by 2. Oh, look at that. All right, so 128 breaks apart into 64 times 2. And what is 64? 8 times 8. So an 8 escapes. An 8. So you could break it down if you wanted to into 8 times 8 times 2. And again, there's your, so same thing. There's your pair of 8s. One gets shot and one escapes. So whether or not you do it the square root way, using perfect squares, or you break it down one more step. But that's what I'm thinking in my head. It's 8 times 8. One gets shot and one escapes. All right, same thing here. We have two baby radicals. We can put them under a giant radical. So 150 over 2, all under a giant radical. What is 150 over 2? 75. So we get the square root of 75. Ooh, 75, 75. What times what is 75? 25 times 3. Very good. And what is the square root of 25? 5 times 5. So a 5 escapes. So we get a 5 escapee, and then the radical 3 stays underneath. What's different about these next two? Yeah, they don't both share the radical. Okay, so now we have a mix of numbers, and they don't mix. It's like oil and water. Okay, but what we can do is I see a radical that I can simplify first. So I need to simplify my radical first. And then I can deal with the regular old numbers. So let's look at here. The square root of 24 breaks apart into what times that? 8 times 3. Can I do 6 times 4? All right, I'm going to do 4 times 6 because 4 is a perfect square. Now this is still all divided by 10, which I can't do anything with yet. So what is the square root of 4? 2 times 2, so 1 gets shot and 1 escapes. So a 2 escapes, and so I get 2 radical 6 divided by 10. Does 6 have any pairs in there? 3 times 2. Nothing matches, right? No pairs. So it doesn't simplify more, okay? Now, though, since we simplified the radical, now I have some regular numbers. And regular numbers I need to reduce, all right? So now I can reduce my regular numbers. 2 and over 10 reduces to what? 1 over 5. We would divide top and bottom by 2. 2 divided by 2 is 1. 10 divided by 2 is 5. And there's still a radical 6 on top. So 1 radical 6 over 5. All right, and then I think I'm good with that. I don't want to do more. Let's go down to the bottom here. Express in simplest form with a rational denominator. Denominator is a better word. Wasn't it so wintry today? Like it was like perfect snow today. All the trees had all the snow on them and everything, you know what I mean? Mm-hmm. I'm just watching it snow right now thinking, oh, how beautiful. Okay, that was a nice little brain break, right? Rational denominator. Radical 2, the square root of 2, is an irrational number, okay? And it is an irrational number because when you put it in your calculator, you get a crazy irrational number. It's crazy. This decimal goes on forever. It doesn't repeat. It has no pattern. Well, patterns don't matter, but it goes on forever and it doesn't repeat. It is crazy irrational. All right? We are not allowed to have irrational numbers in denominators. At least that's what they've said for the past 100 years before we had calculators. So I am telling you now, I think this is antiquated and really lame. But once upon a time, we didn't do this because it was too hard to do. So we didn't want radicals in the denominator. Once upon a time, you actually had to learn how to calculate a square root by hand before these guys. Well, it's just long division. It turns out it's a process almost identical to long division, okay? I had to learn that reading a math book offhand. Like, they don't teach it. They didn't even teach it to me. Not that old. Okay. So, there's a couple ways we can do this, but what I'm going to do is simplify first. All right, I want to simplify 40 first. So I'm going to break it down here. 40 breaks down into what times what? 5 times 8. 5 times 8, true. But 2 times 20? 4 times 10. Why did I choose 4 times 10 instead of 8 times 5 or 2 times 20? 4 is a perfect square. Yes, so I'm going to do a perfect square if I've got one. You're right there, Hayden. Here? Is it here? Here? Oh, I'm there. Okay. There you go. All right. So I'm choosing a perfect square because that's going to be the quickest way to simplify. So if I have the square root of 4, what escapes? 2 escapes. So I get 1 over 2 radical 10. Now 10, does 10 have any perfect squares in it? 5 times 2, there's no pairs, there's no perfect squares, okay? Now, what we have to do here, we've simplified, we must rationalize. And what rationalizing is going to do is it's going to get rid of the radical in the denominator for us. And that's the issue here. We don't want the radical. Is the 2 okay? The 2 is fine. I don't want the radical. That's not okay. So what we're going to do is we're going to multiply top and bottom by whatever that radical happens to be. We're going to multiply top and bottom. Now, why am I allowed to do this? Why am I allowed to multiply by radical 10 over radical 10? What mathematical sense-making allows me to multiply the top and the bottom? What is radical 10 over radical 10? 1, right? What's 7 over 7? 1. What's 100 over 100? 1. What's radical 10 over radical 10? 1. Okay. So if I'm multiplying by what is effectively 1, have I changed the problem I started with? No, because I'm ultimately multiplying by 1. And this is the logic that all math should have, okay? I'm not changing it because I'm multiplying by 1. All right, now what happens here? In the numerator, 1 times radical 10 is 1 radical 10. Here we have 2 times, what's radical 10 times radical 10? No. Let me see, I'm going to write over here. Radical 10 times radical 10. That'd be radical 10 times 10, wouldn't it? They're under 2 baby radicals, so you can put them under a giant one. It's 100. Yeah, it's the square root of 100. What's square root of 100? 10. There it is. So it turns out that radical 10 times radical 10 just gives me 10. It's magical. And maybe you don't remember that. Could you do it in your calculator? Sure. Radical 10 times radical 10. 10. How about that? Okay? Certainly you can check. And so I'm going to clean that up here. We have 1 radical 10 in the numerator. And what's 2 times 10? 20. And there we go. Let's look at number, or this last one here, 4 over radical 7. Now, I had to simplify first. So can I simplify radical 7? No, 7 is prime. Okay, so I'm going to go right to rationalize. Because the goal is no radicals in the denominator. And so what do I need to multiply top and bottom by? Radical 7. On top and bottom, whatever's in the radical. What do I get in the numerator now? Four times radical 7, so 4 radical 7. And what do I get in the denominator? What is radical 7 times radical 7? 7, yes. Can I reduce my 4 and 7? No. It doesn't reduce at all, but if possibly, maybe you'd have to reduce those, question mark, those regular Joe numbers. It's a fraction, does it reduce? But this doesn't. So 4 radical 7 over 7 is a perfect answer. Okay. What's my time? Have I been talking for 30 minutes? Okay. All right. I'm going to leave it at that then. Do you have questions for me? So you do need to ask yourself, can you reduce when you're done? This one would reduce. Okay. So it's a good one to try. All right. You guys have adults math.